Schönen Nachmittag, schönen Abend. Es gibt noch ein paar wenige Plätze da dazwischen drinnen vorne, also bitte die Plätze alle ausfüllen. Wer schnell ist, kriegt noch einen Platz da vorne. Wer sich traut? Wer traut sich? Sehr gut. Ansonsten, wie gesagt, wenn es zu warm wird oder zu eng wird, es gibt unten im Brechtelsaal eine Übertragung von dieser Vorlesung, sodass jeder, der wirklich kommen möchte und zuhören möchte, kann. Gut, lieber Herr Vizerektor Fröhlich, sehr geehrte Damen und Herren, liebe Kollegen und Freunde, lieber Serge, im Namen des Vienna Center for Quantum Science and Technology möchte ich Sie sehr herzlich zu diesem Abend und zu unserer Distinguished Schrödinger Lecture begrüßen. Mich freut es besonders, dass so viele Studenten und junge Leute hier gekommen sind, denn dafür machen wir das ja eigentlich. Wir machen das, um Wissenschaft hinauszutragen, auch über unsere Vorlesungen hinaus und Studenten die Möglichkeit zu geben, Wissenschaft zu erleben und die treibenden Kräfte in der Wissenschaft auch wirklich persönlich kennenzulernen. Vielleicht ganz kurz, was ist das Vienna Center of Quantum Science and Technology, kurz VCQ genannt. Wir haben das vor 2 Jahren gegründet, ein Zusammenschluss von Wissenschaftlern der TU Wien, der Uni Wien und der Österreichischen Akademie der Wissenschaften, die sich damit beschäftigen, was ist denn die Quantenphysik nach der zweiten Quantenrevolution. Die zweite Quantenrevolution ist diejenige, die sich damit dann beschäftigt, die dazu verwenden möchte, Verschränkung und ähnliche Effekte dazu verwenden, um wirklich Technologien zu bauen. Informationstechnologie ist natürlich eine derjenigen, die da im Vordergrund steht. Das VCQ in der Hinsicht bündelt viele der Kompetenzen in Wien und wir sind zurzeit ungefähr 140 Forscher, die in 8 Arbeitsgruppen und 4 assoziierten Nachwuchsgruppen an 3 verschiedenen Standorten in Wien forschen. Dadurch entsteht für die Studenten, für die Graduierten und für die Postgraduierten ein sehr breit gefächertes Ausbildungsspektrum, das wir anbieten und das den Studierenden der MINT-Fächer auf die Möglichkeiten in der Karriere in der Wissenschaft und auch in der Industrie ermöglichen soll. Unsere Forschung wird zu über 80% aus Drittmitteln getragen und das bezieht sich auch darauf, wenn wir unsere eigenen Gehälter mitrechnen. Wir haben zurzeit ungefähr 32 Millionen Euro Projekte und die finanziert sozusagen unser Ding und wir haben eine ganze Reihe von ERC-Grants und Start-Grants und Nachwuchs-Grants, die es uns ermöglichen, diese Wissenschaft überhaupt zu machen. Ganz wichtig, wir haben im letzten Jahr begonnen, ein Nachwuchsprogramm aufzulegen, die sogenannten Vienna Quantum Fellowships, und wir haben die ersten 3 dieser Vienna Quantum Fellows ausgewählt, aus einer Anzahl von 180 Bewerbern, die von den besten Hochschulen der ganzen Welt gekommen sind. Es zeigt, dass Österreich und auch die Universitäten in Wien sehr, sehr attraktiv sind für die besten Leute in der ganzen Welt und sie sehr, sehr gerne zu uns nach Wien kommen und wir sagen, wir haben 3 Angebote gemacht und alle 3 sind gekommen und das ist doch wirklich, hat uns sehr stark mit Stolz erfüllt. Die neuen Fellowships sind ausgeschrieben, wir werden sie im Laufe des Sommers und im Herbstes aussuchen. Es freut mich auch sehr und es freut uns alle sehr vom VCQ, dass Serge Haroche unserer Einladung gefolgt ist, hier Ihnen zu zeigen und vorzustellen, welche Wissenschaft er in den letzten Jahren vorangetrieben hat und die uns alle fasziniert hat. Ich möchte Sie nicht länger aufhalten und möchte dazu als erster dem Herrn Vizerektor Professor Fröhlich das Wort erteilen, ein bisschen etwas über unsere TU zu erzählen und wie das zusammenpasst.
Liebe Kolleginnen und Kollegen, insbesondere Professor Haroche, einen schönen guten Abend. Ich stehe jetzt vor der eigentlichen Situation, dass ich gedacht habe, es ist auf Englisch alles, jetzt muss ich meine englische Rede auf Deutsch übersetzen, aber es wird gelingen hoffentlich. Ja. Ich möchte Sie in diesem wunderbaren Kuppelsaal begrüßen, den wir schon mittlerweile ein paar Jahre als richtiges Juwel haben hier. Wie Sie sehen, das hat eine umgekehrte Schiffform, dieser Kuppelsaal. Das ist so die Bautradition von Kuppeln im 19. Jahrhundert gewesen. Und gegen Ende des 19. Jahrhunderts wurde, was man nicht glaubt, wären wir nicht an dieser Stelle gestanden, denn diese Kuppel war einen Stock tiefer, weil das Gebäude wurde 1890 ungefähr durch Aufbau des zweiten Stockwerkes noch gehoben und eigentlich eine für die damalige Zeit tolle Ingenieursleistung. Und was auch interessant ist, dass zu diesem Zeitpunkt für dieses zentimeterweise Heben dieser Kuppel, die wurde als Ganzes gehoben und sozusagen Schar für Schar dann darunter hochgemauert, wurden Dampfmaschinen eingesetzt, die am Suezkanal zum Bau verwendet wurden. Sie sehen, auch damals hat man schon versucht, Dinge nachhaltig zu verwenden und hat die von Ägypten wieder nach Österreich hergebracht, um sie noch einmal hier einzusetzen. Ja, es ist uns eine besondere Ehrenfreude, Professor Haroche hier zu begrüßen, Nobelpreisträger 2012. Wie schon gesagt, findet die Vorlesung unter dem Dach des Vienna Center for Quantum Physics and Technology statt. Das ist ein Zentrum, wie schon Professor Allmer gesagt hat, das sozusagen die Kräfte von 3 Institutionen, der Universität Wien, der Akademie der Wissenschaften und der TU Wien vereint, die Kräfte und sozusagen die Gehirnkräfte, die Brain Forces der Quantenphysiker. Und es freut mich auch, dass die 3 Gründerväter hier sind, nämlich Professor Schmidtmeier von der TU Wien, Professor Aspelmeier von der Universität Wien und Professor Zeilinger von der Akademie der Wissenschaften. Das ist eine wirklich sehr gute Initiative, weil sie eben das tut, was wir eigentlich tun sollen und manchmal nicht tun, dass man am Standort zumindest zusammenarbeitet. Wie oft passiert es, dass man Kooperationen mit Kollegen in den USA und wo auch immer hat und am Standort selber in der Nähe, wo doch das Gute in dem Fall so nahe liegt, nicht zusammenarbeitet. Begründet wurde das Zentrum vor 2,5 Jahren mittlerweile, ich glaube es war Dezember 2010, wenn ich mich richtig erinnere, da war auch der Kuppelsaal, glaube ich, irgendwie involviert, also zumindest damals hat es ihn schon gegeben und er war in derselben Höhe, seitdem nicht weiter gehoben worden. Ja, wenn ich schon als Leiter für Forschung hier stehe, natürlich möchte ich sozusagen nicht Sie entlassen in den Abend, ohne Ihnen ein paar Worte zur TU-Forschung zu sagen und vor allem insbesondere zur Einbettung des VCQ in die TU-Forschung. Und diese Einbettung ist eine sehr gute und sehr sichtbare Einbettung. Die TU Wien hat 5 Forschungsschwerpunkte, Sie können sie ja lesen, ich brauche sie nicht vorlesen, und einer davon ist Quantum Physics and Quantum Technologies. Und Sie sehen, das passt hier sehr gut rein, denn man könnte fast sagen, das VCQ hat seinen privaten Forschungsschwerpunkt. Es ist de facto ja wirklich so, dass sich diese in Österreich und insbesondere in Wien sehr sichtbare Forschung hier damit sehr gut sozusagen widerspiegeln finden und damit auch entsprechend verankern kann. Die TU Wien hat eine Forschungsmatrix, wo wir versucht haben, in einem Prozess über 3-4 Jahre hindurch Forschungsfelder herauszuarbeiten, wo wir Kompetenzen besitzen und auch nachweisen können in Form von Publikationen, von Projekten, Drittmittelprojekten, eingeworbenen Drittmitteln und von entsprechenden vielen Assistentinnen, Projektassistentinnen und Assistenten, die darauf arbeiten. Und Sie sehen hier, dass Sie in dem Feld der Quantenphysik und Technologie sehr deutlich sehen, dass es hier entsprechende Forschungsfelder gibt, die eben diesen Schwerpunkt letzten Endes dann ausweisen. Das sind die Kompetenzfelder an der TU Wien, in denen sich diese Forschungen hier letzten Endes abspielen. Also die Einbettung ist sehr gut und vielleicht jetzt noch in Form von 2 Slides, ich möchte Sie zu lange aufhalten, noch gezeigt, wie sich das dann äußert in entsprechenden Outputs, in entsprechenden Erfolgen. Und wenn ich zum Beispiel jetzt nehme 2 Slides, die ein bisschen komplementär sind und die zeigen, wo sich hier die Grundlagenwissenschaften und für eine TU Wien dann auch die angewandten Wissenschaften in einem Vektor entwickeln. An der TU Wien gibt es gegenwärtig 13 ERC-Grants, ERC-Preisträger, gemischt Starting Grants und Advanced Grants. Und wie Sie hier sehen, ich habe hier 5 davon mit blauer Farbe sozusagen markiert. Das sind jene, die in der Fakultät für Physik angesiedelt sind. Das heißt, die Physik ist sozusagen unsere Front Faculty, was ERC-Grants betrifft. Obwohl ich auch sehr froh bin darüber und das auch eine sehr schöne Sache ist für unsere Forschungsschwerpunktwahl, dass sich de facto in allen Forschungsschwerpunkten ERC-Grants finden. Und dann habe ich 2 etwas blasser angefärbt und 3 etwas stärker angefärbt. Die 3 sind jene, die eigentlich im VCQ-Bereich im Quantenphysikbereich angesiedelt sind. Das heißt, Sie sehen auch sehr schön, dass sich hier bei uns im Haus auch diese Quantenphysik, diese Quantentechnologie auch sehr stark sichtbar mit Leistungen und mit hochrangigen, in dem Fall ESC-Grants verankert hat. Die anderen beiden, die hier sind in der Physik auch im Bereich Materialien und im Bereich Computational Sciences untergebracht. Also eine hohe Bandbreite, die Sie hier sehen, die sich als Kompetenzbogen der Physik hier aufspannt. Eine TU hat natürlich auch eine angewandte Forschung, eine Aufgabe in Richtung der angewandten Forschung zu gehen. Und ich möchte hier Ihnen als sozusagen auf der anderen Seite des Regenbogens zeigen, was es sonst noch gibt. Das sind nämlich auch vergleichsweise wichtige Kompetenzzentren, Christian-Doppler-Labors, die es in Österreich gibt als Förderlinie, wo Industrie und wo das Ministerium entsprechende Programme fördert, auch lange nachhaltig fördert, bis zu 7 Jahre und vergleichsweise auch hohe Summen. Im Spiel sind wir bei ESC-Grant-Preisträgern und Sie sehen auch hier, dass die Theorie eine Stärke hat. Das heißt, wir haben die Grundlagenforschung und die Translation zur angewandten Forschung und da gibt es dann auch einen sehr breiten Bogen von entsprechenden Themen. All dies trägt dazu bei, dass unsere Mission folgend wir Forschung und Lehre mit dem Ziel betreiben, dass damit Innovation erzeugt wird. Und einer der wichtigen Spieler in der Innovation ist natürlich das VCQ und wird es auch in Zukunft sein. Ich freue mich schon sehr auf den Vortrag von Professor Haroche, wünsche Ihnen einen spannenden Abend und nochmal danke, Herr Professor, dass Sie zu uns gekommen sind.
So, danke, Herr Vizerektor Fröhlich. Und ich darf jetzt bitten, Arno Rauschenbeutel, der bei Serge Haroche studiert hat und promoviert hat in Paris, ihn vorzustellen.
Ja, auch ich heiße Sie herzlich willkommen zu dieser 3. Schrödinger Vorlesung des Vienna Center for Quantum Science and Technology. Mein Name ist Arno Rauschenbeutel und ich freue mich sehr, dass Sie so zahlreich erschienen sind. Ich möchte auch noch einmal durchsagen, dass, wenn Sie sitzen möchten, Sie im Erdgeschoss im Prechtl-Saal auch die Vorlesung live übertragen bekommen. Ja, und außerdem freue ich mich sehr, Ihnen unseren heutigen Gast, Serge Haroche, vorstellen zu dürfen. Serge Haroche wurde 1944 in Casablanca, Marokko, geboren. Er ist Absolvent der Ecole normale supérieure in Paris und promovierte 1971 unter der Anleitung von Nobelpreisträger Claude Kontanoudji an der Pariser Universität Nummer 6. Im Anschluss verbrachte er 2 Jahre als Postdoc an der Universität Stanford. Dort arbeitete er in der Gruppe eines weiteren Nobelpreisträgers, Arthur Charlow. 1975, also im Alter von nur 31 Jahren, hatte er einen Ruf auf eine Professur an der Universität Paris Nummer 6 und diese Position hielt er bis 2001 inne und dann erhielt er einen Lehrstuhl für Quantenphysik am Collège de France. Dazu ein paar Worte: Das ist eine der Forschung und Lehre gewidmete Institution in Paris, die in der Art einmalig auf der Welt ist und in Frankreich das höchste Prestige aller wissenschaftlichen Einrichtungen genießt. Und außerdem ist Serge Haroche seit 2012 Präsident dieses Collège de France. Darüber hinaus war er Gastprofessor an der Harvard-Universität und er hatte eine Teilzeitprofessur an der Yale-Universität. Seine Forschung und Experimente hat Serge Haroche vorwiegend am Castres-la-Bruxelles-Labor der École normale supérieure durchgeführt. Sein Hauptforschungsgebiet ist die Hohlraumquantenelektrodynamik. Das ist ein Gebiet der Quantenoptik, in der die Wechselwirkung zwischen Atomen und Photonen untersucht wird, die in verspiegelten Hohlräumen gefangen sind, und mit diesem System ist es ihm und seinen Mitarbeitern gelungen, zahlreiche grundlegende und überraschende Eigenschaften der Quantenmechanik experimentell zu demonstrieren und zu erforschen. Für seine Arbeiten hat Serge Haroche zahlreiche Preise und Auszeichnungen erhalten. Einen vorläufigen Höhepunkt fand seine Karriere im Jahr 2006, als er die Goldmedaille des französischen Nationalen Zentrums für wissenschaftliche Forschung erhielt. Die höchste wissenschaftliche Auszeichnung, die man in Frankreich erlangen kann. Die Krönung folgte dann letztes Jahr mit dem Nobelpreis für Physik, den er gemeinsam mit dem Amerikaner Dave Wineland verliehen bekam. Begründet wurde der Preis mit den bahnbrechenden experimentellen Methoden, die von den beiden entwickelt wurden und mit denen man einzelne Quantensysteme messen und manipulieren kann. Heute wird Serge Haroche nun über diese Experimente berichten und uns in die wunderbar widersprüchliche Welt der Quantenmechanik entführen. Ich wünsche Ihnen eine spannende Reise. Bevor es aber losgeht, möchte ich mir erlauben, noch ein paar persönliche Worte an Serge Haroche zu richten. Serge, it is an immense pleasure for me to announce you as our distinguished lecturer today. We met 16 years ago at the spring meeting of the German Physical Society in Mainz. At that time you gave a plenary talk, and I was a student of Dieter Meschede, who was looking for an exciting PhD position. I later on found that position in your group. The title of your talk in Mainz at that time was Observing the Decoherence of Schrödinger Cat States of Radiation and Exploring the Quantum Classical Boundary with Single Atoms in Cavities. Actually, this could also be the title of today's talk, which of course does not mean that no results have been obtained since then. On the contrary, over the past decades, you and your co-workers realized the most beautiful demonstrations of the counterintuitive properties of quantum mechanics. With your experiments, you inspired a whole new generation of researchers, and that includes me, which now consider themselves as quantum engineers. You thereby gave an enormous impetus to physics. You cannot imagine the joy it gives me when I see that all these achievements have been duly rewarded. The joy to announce you as the Nobel Prize in Physics. Serge, we are looking forward to your talk.
So thank you very much, Arno, for this very kind introduction. I am very pleased to be here today and to have this opportunity to talk about the work which we have been realizing in Paris over the last, as you said, 16 years or so. Many of you know that we have been in this experiment trying to raise various ersatz of Schrodinger cats, which are suspended between different states, and so it's quite, I think, it's quite appropriate for a Schrödinger lecture, and I'm very honored to have this, the pleasure to deliver this lecture here today. You see on this slide two hands which are juggling with balls between two mirrors. In fact, these balls represent photons, and I like this picture because it shows that what we are trying to achieve is to observe photons in a gentle way without destroying them, and trying to control this field and to prepare these photons into some kind of strange state and be able to keep them into this state as long as possible. By doing so, we think that we are in fact realizing some modern versions of the thought experiments that the founding of quantum physics had imagined back in the 1920s. And at the same time, we realize steps for quantum information procedures. So as you said, we can consider ourselves as some kind of quantum engineers, although I don't like too much to mix basic research with engineering, and as we will see in the talk, there are still some open questions about that. So what I also want to say is that in this field, as we often say, we are seeing the world from the shoulders of giants, and the people who founded quantum physics 100 years ago had developed the concepts that we are using in these experiments today. And I believe it's appropriate to start with some historical reminiscences, especially because this month, April 2013, is the 100th anniversary of the Bohr model of hydrogen atom. It's exactly 100 years ago that Bohr applied for the first time the idea of the old theory of quanta for a material system. Of course, the story had started before especially by Einstein's paper in 1905, where he figured out that light waves are quantized in terms of photons. But then 8 years later, Bohr found out that electron orbits in atoms are also quantized, involving the same quantum of action, the Planck constant. And then from this kind of work emerged a strange world in which matter and waves are blurred into a kind of ambiguous concept, and this led to discussions which culminated into the emergence of the quantum theory in the 1920s. At that time, people like Bohr and Einstein kept discussing to find out what sense could be made of this world where matter and waves were blurred, where the superposition principle applied. So I would like in the first part of the talk to remind us of these steps, especially because the kind of atoms I am using in my experiments are very close to the Bohr atom of the old theory of quanta. We're using circular atoms in which the electron is going around the core like a planet around the sun. And we are doing this experiment in a box which reminds the Einstein-Bohr photon box of the thought experiments of the 1920s. So let's start with Einstein, of course, who introduced the photon into physics. I remind you that everything started from a very disturbing fact, the fact that heated bodies had a spectrum which could not be explained classically. The spectrum of heated body presented a maximum at a given temperature for a given frequency, a bell-shaped curve, which could not be explained by classical physics. If you tried to explain by classical physics, you find the ultraviolet catastrophe. The intensity was increasing with frequency without limit. And of course, Planck had started to give an explanation because he found out a formula which gives the exact shape of the blackbody radiation, but its formula was was introducing a quantization of the field which was rather formal and mathematical. It's Einstein in 1905 who made a brilliant analogy with another bell-shaped curve, the fact that the distribution of velocities of a gas in a gas cell obeys to a bell-shaped curve, which looks very much like the bell-shaped curve of the radiation field, led by comparison Einstein to conclude that light is made of quanta, like an ensemble of atoms is made of discrete particles, and it introduced this quanta of energy, E equal h nu, which were later called the photons. So this started the story in 1905, and as I said, 8 years later, Bohr applied this quantization to the orbits of atoms, the orbit of electrons in atoms. The nucleus had just been discovered by Rutherford, and Bohr was a postdoc in Manchester in Rutherford lab, and he described an atom which was a planetary system, but he introduced the fact that the orbits in this planetary system were stable only if they corresponded to a quantized angular momentum. And in this case, the angular momentum is just the product of the mass of the electron by the velocity and the radius of the orbit. And if this quantity is just an integer number of Planck's constant, he was able to show that the radii of the orbits increase as the square of integer numbers, and that the energies were of these states were inversely proportional to the square of integer numbers, introducing the Bohr radius, which was a combination of electric charge, mass, and Planck's constant, and the Rydberg constant. He was able also to compute it. The Rydberg constant in particular had been introduced in physics before by Rydberg and Balmer, who had found empirically that the spectrum of hydrogen obeyed to very simple mathematical laws with integer numbers, but Bohr was able to explain that with his quantization of the electron orbits, and so it was a huge step because it was the first time the quantum laws were applied to a material system. Now this became even more obvious another 10 years later when De Broglie introduced the concept of matter waves. De Broglie made another jump. Here he said that not only you could say that light waves were made of discrete particles, but inversely, particles were also waves, and you can associate to a particle, for instance, an electron of velocity v, a wavelength lambda equal to h over mv. And the Bohr quantization then became very simple. The condition for quantizing the angular momentum just meant that you need to have an integer number of de Broglie wavelengths around the circumference of the orbit, which means that, in fact, this orbit is just a kind of running wave going around the core, running wave which need to have an integer number of this de Broglie wave to be stable. And so, in this way, De Broglie gave an interpretation of this atom, making the wave and the particle aspects the two sides of the same coin. So if I summarize these early theories of quanta, which have started by the fact that light waves are quantized, that electronic orbits in atoms are also quantized, and that this suggests that electrons are also waves, this led step by step to the progressive lifting of the great veil. This is a sentence that Einstein used in a letter to Langevin when he got the thesis of De Broglie, the fact that this kind of matter-wave dualism was really lifting the mysterious veil which was hiding to us the microscopic world. And of course, this lifting of the veil was completed by the work of Heisenberg, Schrödinger, and Dirac in the mid-1920s, where the full-fledged quantum theory was developed. So this introduced a world of wave-particle duality, and of course this duality introduced the superposition principle into physics, challenging our classical ideas about determinism and about the physical reality. To illustrate that, we all know that the Young double-slit experiment is very revealing. I remind you that this experiment consists in sending particles through two slits and looking at the fringes which are produced downstream. And you see here on the right part of the screen an experiment which has been done many times with photons, but which can also be done with electrons or with atoms. When the particles cross one by one the system, you see that you have impacts on the screen. At the beginning they seem random, but then they build up statistically a set of fringes, bright and dark fringes, and this interference pattern is very impossible to understand in classical terms. It's clear that if particles cross the apparatus one by one, classically they would have to cross through one slit or the other, and if they did that, there is no reason why they should not be able to get to any point on the screen. The fact that they always miss dark fringes means that in some way they know that, quote unquote, that the two slits are open at once. So it means that you have to give up classical trajectories and you have to admit the superposition principle, which I write here by using this wave function formalism. The state of the particle is at the same time going through the left slit and the right slit. And of course, to make sense of this, Bohr introduced this principle of complementarity. The particle and wave aspects are two exclusive sides of the same coin. Which aspect is observed depends upon the experiment you do. If you try to find out that the particle went through one slit or the other, you will find it out, but then you will not see fringes. And if you are not able to find out, then you will see the fringes. So this principle emerged from discussions with Einstein, and one of these discussions took place at the Solvay meeting of 1927. Einstein was always a devil's advocate in this debate. He tried to find a loophole, he found defects in the quantum theory, and for instance, he imagined a Young double-slit experiment in which the upper slit would be a very light system which would be able to recoil under the collision with a particle. And so what Einstein said is, listen, if you want to find out through which slit the particle went, just try to detect the momentum transfer to the movable upper slit. And the slit will start to move after the particle has crossed, so you will see the fringes and you will know that the particle went through one slit or the other. But then Bohr said, listen, if you want to find out the transfer, you have to define the slit initial momentum with very high precision, so with a very small delta t. Hence, according to the Heisenberg uncertainty relation, delta x will be large, and if delta x is large, you will have a blurring of the path difference because you will not know where exactly is the upper slit. And this uncertainty is exactly what is needed to classically suppress the fringes. So you see, this kind of argument was developed in 1927, and at that time it was not yet fashionable to talk about entanglement, but the notion of entanglement was looming above this argument in a very simple way. Let's consider what does it mean to have an interference? It means that the particle crosses the upper slit and the lower slit at the same time. It's in a superposition. But if the upper slit is very light, then you have a correlation. If the particle crosses the upper slit moves, and if the particle crosses the lower slit, the upper slit does not move. And so you see now that the quantum system, which is made up of the particle plus the slit, is an entangled system. You cannot describe the particle without describing the state of the slit at once. And according to the modern description, what happens is that if you want to find out what is the state of the particle, you have to trace over the state of the slit. And if you do that, you lose the state description. What you have is a density operator for the total system. This is a technicality, but for those who know about that, it's quite clear that this entanglement kills the coherence in the system because you don't have a wave function anymore for the particle. So that was a discussion in 1927. Then 3 years later, at the Solvay meeting of 1930, Einstein came up with another thought experiment. This time he challenged the other Heisenberg uncertainty relation between time and energy, the delta E, delta T larger than h bar relationship. He tried to imagine an experiment in which you could beat this uncertainty relationship, and this is the famous photon box experiment. He assumes that you can trap a field in a box which is paved by perfect mirrors, and then you have a clock which allows you to open a shutter during a very short time interval. And what Einstein said that let's weigh the box with arbitrary precision before you let a photon escape. And to weigh the box, you just weigh it in the gravitational field of the Earth, so you have to suspend masses and look at and use the E equal mc squared relation to find out what is the energy which is stored inside the box. Then you let the photon escape during an arbitrary short time interval, and then you remeasure, and you take all the time you want to remeasure after that, and so you could beat the delta E, delta T relationship. Bohr was very unpleased by that, and he took him some time to find where the problem was, and what he said is that be careful with the measurement of time due to the box motion in the gravitational field. If you have to put weight into the box will move up and down in the gravitational field, and the redshift will affect the precision with which you will read the timing of the shutter opening, and if you do it carefully, you find that exactly what is required to restore the Heisenberg uncertainty relation. I don't want to enter into this argument, which some people have found difficult to follow, but I want to stress the fact that this photon box experiment involves a clock which is timing the escape of light quanta, and we will come back to this idea in a different context later on when I will describe the experiments that we have been doing during the last years. So the last thought experiment I would like to talk about is the Schrodinger cat experiment, which is more like a metaphor. It's described in less precise terms than the other ones, but as you all know, it involves a cat which is trapped in a box with a single atom. The atom is put in a kind of superposition between two states. One state leaves the cat alive, but if the atom is in the other state, it triggers a system which kills the cat. So if the atom can be in a state superposition, it means that the cat can be also in a state superposition. And you see that this superposition involves entanglement, and in fact this metaphor was described by Schrödinger in a paper in 1935 where he discussed for the first time entanglement in detail. As I said, entanglement was already implicit in quantum physics before, but Schrödinger put it really in precise terms in this paper. And he also used this to explain the difficulty there was to export quantum laws into the macroscopic world. In fact, this system is a kind of amplifier. You have a small system in state superposition. If you couple it to a large system, the large system has to be also in a state superposition, and this raises problems connected to measurement theory and so on. I will come back to this later on. So these are the thought experiments of the 1920s, and it's interesting to reflect on what the founders of quantum theory thought about all these thought experiments. And in fact, it's well known, there are two quotations, very famous quotation by Schrödinger in 1952. In one of these quotations, he said, "We never experiment with single electrons, atoms, or small molecules. In thought experiments, we assume that we do, and it always results in ridiculous consequences." So I don't know what to make of this, but it seems to imply that he thought that these experiments would never be possible. Of course, when I read that, I was puzzled, because in 1952, Schrödinger must have known that you could detect single particles. In fact, bubble chambers, cloud chambers, accelerators already did exist at that time. But as Schrödinger said, this was, in fact, this detection was through post-mortem observations. You are looking at the remnants of traces left by these particles after they had decayed. So in fact, he was considering particle physicists as paleontologists who were looking at the bones left of past events. And to make this clear, he also said in the same paper, "It is fair to state that we are not experimenting with single particles any more than we can raise ichthyosauria in the zoo. We are scrutinizing records of events long after they have happened." So this again seems to imply that he did not believe in this experiment to be possible. In fact, these two papers these two quotations come from a series of two papers which have a very interesting title. The title is "Are They Quantum Jumps?" In fact, he was doubting that quantum jumps could be observed. And this has, of course, to do with the fact that Schrödinger's equation is a continuous equation which describes a unitary evolution, and quantum jumps are not in the Schrödinger equation. We will come back to this later on in the talk. So, of course, you know that things have changed since then, and now we can control a zoo of particles in real experiments. And this has become possible because of technologies which did not exist at the time of even in 1952. One of them, and I think the most important one, is the development of tunable lasers. The lasers have really revolutionized atomic physics and quantum optics, and if you think of all the marvelous things that we are doing now, with experimenting with single photons, experimenting with cold atoms, experimenting with new states of matter, which are the Bose-Einstein or Fermi-degenerate gases, doing extremely precise experiments with fantastic atomic clocks, all this would have been impossible without the development of tunable lasers, which allow us to manipulate with an exquisite precision the internal and external degrees of freedom of atoms. The second invention, which is of course necessary for all this, are fast computers. The correlations that you have in the systems, atoms or photon states, are correlations occurring at a very fast rate, and you need computers which have the memory and the ability to compute in real time if you want to keep track of all these correlations. And for some experiments, including ours, you need also the development of superconducting materials to make very highly reflecting mirrors. What I want to say is that it's very interesting to note that all these technologies are quantum. In fact, you could not have developed the lasers, the computers, the superconductors without a knowledge of the quantum world. So in fact, the story is going full circle. From the quantum principles, you develop technologies which allow us to do experiments that the fathers of the theories thought would be impossible to do. So what are we doing? In fact, so as you said, the quotation for the Nobel Prize of last year was particle control in a quantum world. And what Dave Weinand and my group are doing are, so to speak, the two sides of the same coin. We are trying to manipulate non-destructively single atom with photons in the case of ion trap physics, and single photon with atoms in our case. And these two experiments are symmetrical of each other. So in one experiment, ions are cooled down with lasers, and you look at the light that the laser that they They scatter from laser beams to get information about the ions. And we do the opposite. We trap the photons and we send the beam of atoms and we extract information from the atoms. In both cases, we try to do in vivo physics by opposition to the post-mortem physics that Schrödinger was talking about. And in both cases, we are exploiting the light-matter interaction at the most fundamental level. For the specialist, what we are using is a Jaynes-Cummings model, which describes how a two-level system interacts with a mode of the field. And this Jaynes-Cummings model is exploited in ion trap as well as in cavity QED. Now, I want also to stress that this physics is being carried on in many groups in the world. And we have been selected for reasons which are beyond our knowledge, but we are considering that we are representing a field, very active field of people who are working with ions, with photons of various kinds, photons in cavities or photons propagating in free space or in fibers. All these experiments try to control quantum system to demonstrate quantum principle or to achieve steps for possible application in the future. I just will give one example from ion traps and then shift to my field, which is the photon traps. This is an example showing 5 ions, 5 beryllium ions in David Winant's lab at NIST, and he has been able to do quantum computing steps with that and to prepare Schrodinger Cat state of these ions by putting them in state superposition. This was about 12 years ago. Last year in Innsbruck, the group of Rainer Blatt has been able to manipulate 14 ions in a trap. And I show this just as an example of the huge space which is open for quantum system if you can control even as few as 14 ions. If each ion has 2 inner quantum states that you can represent as a spin pointing up or down, you have one state in which you have prepared all the spins up, but you can also consider states in which one of these spins is down, or states in which 2 spins are down, or any combination up to the point where all the spins are down. And it's, of course, there are 2 to the n states of this kind, and not only you have this 2 to the n state, but any combination, superposition of this state is possible. So you have a huge space of possibility, superposition with arbitrary amplitudes for these 2 to the n terms, and this, of course, allows you to store much more information than in n classical two-level system, in n classical bits. And this is explains all the power of quantum information as opposed to classical information. If you take a system which contains 50 of these particles, such system cannot be simulated by classical computers. Schrödinger equations that you will write with the 2 to the 50 amplitudes would never be solved classically. But now we are at the point where one could manipulate these 50 particles, for instance, put 50 atoms at well-defined points in an optical lattice, and have this system interact through an Hamiltonian that you could engineer. And in this way, people are thinking about quantum simulators, or maybe one day quantum computers, and they put a question mark. The difference that the quantum simulator is doing some kind of analog computation, simulating the system, whereas a quantum computer would be able to achieve algorithm, to perform algorithms according to a planned program, and this would raise a lot of problems. So I just wanted to say this to explain why this field is exploding. This hope to be able to manipulate quantum logic and make it useful has certainly fueled a lot of money into the field. Now I will go to what we are doing in Paris, and our field is cavity quantum electrodynamics. That is, we are trapping photons in cavities and using Rydberg atoms to study them. And we like to think of this, especially in this year, 2013, are exploiting Bohr's atom in Einstein's photon box. So this shows in very simple terms how we do the experiment. We have 2 mirrors. These mirrors are exceedingly highly reflecting. They are copper mirrors which are machined with high precision, and we have spotted a thin layer of niobium on the mirrors. They are cooled to very low temperatures. The niobium is superconducting, has a very high reflectivity. And we send a circular atom, a Bohr atom, between these mirrors, and this Bohr atom interacts with the field inside the cavity. Now, to give you a few figures, the light is bouncing more than 1 billion times on the mirrors, and if you unfold the trajectory of a photon, it makes about 40,000 kilometers, which means that it takes more than 1/10 of a second for the photon to disappear. 1/10 of a second is a time which is the shortest time for our human perception, but for a photon it's a very long time. You see, it can travel over a long distance, and you can have thousands of atoms interacting with the same photon, and so we can perform a lot of quantum information and quantum tests with the system. So you see here a movie which shows how the experiment works. The atoms are going one by one, and after they have crossed the cavity, we destroy the atom, and I will say in a moment how we do that. And from this destruction of the atoms, we get information about the field. The field is not destroyed. That's the atom which are destroyed, and so we try to protect as much as we can the field inside, and we use information which is imprinted on the atoms crossing the cavity. So what kind of atoms do we use? Usually we call that the circular Rydberg atoms, but for this talk I add Rydberg-Bohr atom because I want to emphasize that it's really the Bohr atom of the circular Bohr atom. So we start from an atom in ground state, and we use lasers and circularly polarized radio frequency photons to feed energy and angular momentum into the electron. And we get an electron going around on a circle, on a giant orbit, which has a size of about 1/10 of a micron in diameter. This method has been pioneered by Dan Kleppner in 1983 at MIT. And as I have shown to you before, you can think of it as a running de Broglie wave, which has an integer number of de Broglie wavelengths around the circle. And this number of de Broglie wavelengths is just the principal quantum number in our system. Now, we will see that in many applications, in many experiments, we need an electric dipole. And you see that such an atom has no electric dipole because the running wave around the circle has a uniform amplitude, and so the center of gravity of the electron is at the nucleus. If you want to prepare an electric dipole, what we can do is to apply a pulse of microwave which admixes two levels with 50 and 51 de Broglie wavelengths. And then you get a classical interference. The two waves add at one end of the orbit, and of course, since you are skipping one node, they subtract at the other end, and you get a kind of crescent which is rotating at 50 gigahertz. So this is even more classical. You make a wave packet which rotates, and this is a planetary atom. It's an atom which has a density of electronic density going around at 50 gigahertz. And you can think of this electric dipole as a hand of a clock which revolves around the nucleus. And in fact, this picture is useful. In fact, we will build with the system a Rydberg atomic clock, and the perturbation of this clock by light will be the signal which we'll be using in most experiments. Last technical point, how do you detect these Rydberg states? They are detected by field ionization. You see on the left the Coulomb potential with the two levels, E and G, the upper and the lower state of the transition between the Rydberg states, and they are both bound. If you want to detect the atom, you apply an electric field which adds to the Coulomb potential a linear potential, which has the effect of lowering the barrier and by controlling the amplitude of this electric field, it is the slope of this line, you can lower the barrier to the point where the upper state escapes and the lower state remains bound. And if you apply a ramp of electric field, you see that the field will reach the threshold for ionization at different times for the upper and the lower state. And so you will be able to discriminate by destructing the atom, you will be able to discriminate in the current the upper and the lower state. And if you want to use the language of quantum information, each atom provides a bit of information. You will find in the end the atom in state E or in state G, depending upon where it is ionized. And so each atom gives you a bit of information about the field that it has experienced when crossing the cavity. So what about entanglement? In fact, this system is a machine to entangle the atom to the field. Suppose that the atom and the cavity are resonant. You start with an excited atom in state E and the cavity empty. After some time, the atom will emit a photon, go from E to G, and leave a photon in the cavity. But if the cavity is very good, the photon will stay there to be reabsorbed at a later time, and you will have an oscillation between E0 and G1, which is called the vacuum-Rabi oscillation. And this oscillation occurs at a frequency which in our experiment is 50 kilohertz. So at a rate of 50 kilohertz, the atom and the cavity field play a kind of ping-pong game, exchanging their energy periodically. At an arbitrary time, you are in a linear superposition of E0 and G1 with amplitudes given by the cosine and sine of this omega t over 2 parameter. You see that there are some times which are very interesting. If you interrupt after omega t equal pi, you go from E0 to G1. In this case, you have no entanglement, but what you have done is to exchange the excitation between the atom and the field. And you can think of the field in the cavity as a kind of quantum memory. You can imprint the state of the atom into the field and let the field in the cavity until another atom will pick it up. So you can use the atom, the field as a kind of what is called a quantum bus or a quantum memory, which will allow us to link atoms together. And we'll see an example of that in a moment. Another very interesting situation is if the atom emerges from the cavity when omega t is equal to pi over 2. In this case, the two amplitudes are equal, and then you have an entanglement between the atom and the photon, which means that you have a superposition of an excited atom leaving a cavity empty, plus a de-excited atom leaving a photon behind. And in principle, even if the atom travels for kilometers, this entanglement will survive at a long distance. We did not perform any non-locality test because the atoms are too slow for this kind of thing, but basically this system is a system to demonstrate non-locality. It's just a matter of technology and trying to improve on that, and we will see that there are systems in which this kind of test can be done, which looks like cavity QED. So I will just give you one example. Here, how can you entangle a pair of atoms? You have your cavity and you send across the cavity two atoms. The first one is excited, E1, and the second one is in the lower state G. And you control the time during which each atom interacts with the cavity by applying an electric field across the mirrors. This electric field, by Stark effect, will tune each atom in resonance with the cavity for a given time. And you can choose the time corresponding to a pi over 2 pulse or the time corresponding to a pi pulse. So for the first atom, you realize a pi over 2 pulse. And then for the second atom, you realize a pi pulse. And if you do that, it's clear that you will entangle the two atoms. The first atom starts with the cavity in vacuum. So you go from E0 to a superposition of E0 and G1, while the second atom is still in state G. And then the second atom, if there is no photon, the second atom will stay in state G. But if there is one photon, the second atom will get excited and the field will go back into vacuum. So you see that you have mediated the interaction by the photon, and you get an entangled pair of atoms which are maximally entangled, and you can play the games of not Bell's inequalities because of the fact that they are very close apart, but you can show that you have correlations between these two atoms in any basis. You can play this game further. You can show that you can build quantum gates with atoms and photons as qubits, that you can build the entanglement carry this entanglement to 3 atoms and build entangled state of 3 atoms as a Green-Berger, Horn, and Seilinger type. We did an entangled state of 3 atoms in this way. So you see that you can use this as a tool, use the cavity field as a tool to neat entanglement between atoms. I don't carry this further because you will not convince people that with flying qubits you will build a computer. But later on I will show to you that now these experiments are done with circuits, in circuit QED, with Josephson devices, and then this becomes serious. But let's go to another issue now. Suppose that you have delivered a photon in the cavity. How can you tell that you have a photon inside without destroying the photon? So I will describe very briefly how we can photons in the box without destroying them, and how we can observe when they escape from the box, that is, the quantum jumps of the field. For that, I start by remarking that this is not the usual way photons are detected. In the usual world, when you detect a photon, you kill it. When you look with your eye, the photons which are received on your retina are destroyed, and any detector, except the one I will be describing to you now, is killing the photons. So after the photon has been detected, if you had one photon, the click tells you that you are back in vacuum. This is a photoelectric effect. The photon is transformed into an electric current and is away. So the photon dies. But this is not what quantum physics tells us about an ideal measurement. Ideally, if you measure something, you should be in the eigenstate of the measurement afterwards. So if you believe into quantum physics and what you learn in textbooks, if I measure one photon and if I find one photon, if the measurement is the right one, I should have one photon left after that. This is called quantum non-demolition, and it's very not obvious to do it with photons. And the pioneer in this field was Vladimir Barginsky, who invented ways to use polarized matter to detect photons without destroying them. And it is exactly what we do. We use polarized big atoms, Rydberg atoms, to detect photons without destroying them. We need a detector which is a non-demolition detector at the single photon level, which is able to take an imprint of the photon without absorbing it. And we need a very good box to keep the photon alive long enough to be able to reproduce the experiment many, many times. So I talked about the box already. What about the non-demolition detector? This brings me to something which had been discovered by my thesis advisors, Claude Cohen-Tanouji, the light shift effect. We need an atom which interacts with the field without absorbing it. So we need a non-resonant atom. There will be a detuning delta between the atom and the cavity, so the atom will not be able to absorb light. But in this case, the energies of the atomic system are slightly altered by the light shift effect. And I show you here what happens. You see here the energy levels E and G of the atom as they cross the cavity. And when the atom enters in the cavity, state E is shifted in one direction, and the state G is shifted in the opposite direction. These shifts are given by very simple quantum physics. They are proportional to the square of the coupling, inversely proportional to the detuning, and proportional to the intensity of the light, that is to the photon number. So you have, this is the only formula you need. You find that shifts in opposite direction for state E and G, which means that if you have prepared a superposition of E and G, the phase that this superposition will accumulate while the atom crosses the cavity will be the integral of this shift, which I have written here. So it's integral of omega squared over 2 delta times dt. dz over v is just the time the atom takes to cross the cavity. So you integrate and you get a phase shift per photon, phi naught, which can be as large as pi because of the very strong coupling of these huge atoms to the microwave field. So what does it mean? It means that if you achieve this pi phase shift per photon, and if you prepare a state superposition, and if there is 0 photon in the cavity, the dipole will exit in one direction, and if there is 1 photon in the cavity, the dipole will exit in the opposite direction. This is a pi phase shift. And if you are able to measure this phase shift, you will count the photons, and you will count them in a non-destructive way. So I think there is a good symmetry here, because here I introduced you the legacy of my thesis advisor, Claude Cohen-Tanouji, and the next slide I introduce the legacy of Dave Wineland's thesis advisor, Norman Ramsey, which is the Ramsey interferometer. The way to measure phase shifts is to build an interferometer, but this time an interferometer which acts in time and not in space as a young one. So you see what happens here. You have the field that you want to measure in this cavity. Here you have the box in which the circular states are prepared. So our Bohr atoms are crossing this box one by one. They are detected here by state selective field ionization, which means that the atom exits in one state or in the other, and we get just this binary information per atom. And you have two other important ingredients here, which I have shown here. You have a cavity, an auxiliary cavity R1 before the atoms enter in the cavity C, and an auxiliary cavity R2 here. The first cavity prepares a state superposition. It had mixed E and G. Then the atom crosses the cavity, accumulates a phase shift, and the second cavity applies another flash of microwave to detect the direction of the dipole after the atom has crossed the cavity. Now, the succession of these two pulses makes up a Ramsey interferometer, and it describes in time what the Young double slit does in space. It will give you fringes when you will look at the probability for the atom to be detected in one state or in the other downstream. So what we are building, in fact, and of course this Ramsey interferometer is used in all atomic clocks. So what we have built here is an atomic clock which is delayed by the photon trapped inside. You see here the fringes that you would get if there is 0 photon in the cavity. And if you have a pi phase shift per photon, it means that when you have 1 photon in the cavity, the fringes are translated by half a fringe interval. So you see that if you now choose the frequency of your interferometer to tune it at the maximum of the red fringe, you are at a minimum of the blue fringe, which means that at this point, an atom will exit the cavity in one state if there is 0 photon, and the other state if there is 1 photon. And you see exactly what happens on the next slide. The blue bar means that the atom is in state G, the red bar in state E, and you see this kind of trace occurring in real time. And you see immediately that when a photon appears in the cavity, you see it as a change, sudden change of the probability for the atom to get out in one state or in the other. And you see that this photon survives for about half a second and then disappears in another quantum jump in the opposite direction. You see that hundreds of atoms see the same photon, so it's really quantum non-demolition. You can also say that this is a quantum gate. The photon plays a role of a control qubit which decides what will be the state of the other qubit, which is the atom, without changing its own state. So this is the definition of a gate. And you see that the Ramsey interferometer is very useful for quantum information. Not only in cavity QED, in ion trap physics also, this game of Ramsey pulses is used to build quantum gates in a very efficient way. You can also count larger photon numbers. If you have more than 1 photon in the cavity, of course you need more than 1 atom, because 1 atom gives you a bit of information. But we have been able to show that by sending atoms one by one across the cavity, you acquire information progressively. You see here, we start from a field, we don't know how many photons we have in the cavity. So we have a flat histogram between 0 and 7 photons. In fact, what we have done is to inject a small coherent field, which is a superposition of different photon numbers. And then we send atoms one by one, and the computer, which gets the information from the experiment, is able to update the photon number distribution step by step. And you see that in this realization of the experiment, the photon number hesitates between 4 and 5 photons, and then decides that there is 5 photons in the cavity. And then it stays flat, because once you have obtained this value, according to quantum physics, you stay in this state. In another realization of the same experiment, you find now 7 photons instead of 5. And of course, you find when you do the experiment again and again, you find a very obvious, very fundamental result of quantum physics. The result of a measurement is random. This randomness is inherent to quantum physics, and it's even deeper than that. One way of interpreting this would be to say we don't know how many photons we have in the box, but we learn it by making the experiment. But in fact, it's not that. At the beginning, the photon number has no meaning. We are in a superposition, a coherent superposition of different photon numbers. So the photon number does not exist before the experiment is done. It's not just the fact that you don't know. There is no photon number. The photon number is produced by the experiment in a random way, which is really what quantum physics is about. And if you do it on many, many realizations, you reconstruct the histogram of the Poisson distribution that you need in a coherent state. You can also go on measuring on a longer time scale, and you see that the field collapses. You repeat the measurement, so you stay in the same state, but of course, since your cavity is not perfect, you start losing photons, and you see quantum jumps as the field decay back to vacuum. So we have analyzed a lot of these trajectories, and you see here several examples of quantum trajectories which show that if you observe the field escapes in steps. And these are quantum jumps. And again, this brings me to the question that Schrödinger asked, are they quantum jumps? And you see the answer is yes, they are quantum jumps. But of course, you have quantum jumps because the system that you are studying is not isolated. The quantum jumps occur because you have coupled your system in the cavity, you have coupled it to a measuring device, which is a stream of atoms. And this is this coupling which introduces the irreversibility and the jumps. If you look at the Schrödinger equation by itself, there are no jumps, because the Schrödinger equation describes a statistical average over many, many realizations. And in fact, if you average these staircases over many, many realizations, you find an exponential decay, which is what is expected from the Schrödinger equation or the generalization of Schrödinger equation to dissipative systems. So we have measured thousands of such trajectories. You see here you have something which looks strange. You have a jump up. This is because we are not at 0 degree. We are at a finite temperature, and sometimes a thermal photon appears in the cavity and then disappears. So we can measure with very high precision the temperature of our field with this kind of experiment, and we can make the statistics of the length of all these stair steps. And when you do that, you find that the lifetime of the n photon state is a cavity damping time divided by n, which means that the higher you are in the scale of your harmonic field oscillator, the shorter is the lifetime of the state. And this brings me back to the Heisenberg-uncertainty relation I was talking about. So we have a photon box. We know when we can measure when the photon escape. Do we satisfy the Heisenberg-uncertainty relation? And the answer is yes. If you have n photon in the box, what is the uncertainty in the energy? You have n quanta of energy h bar omega, and the Q of the cavity, which gives you the width of the precision with which you can measure this frequency, means that the width of the cavity is omega over Q. So the uncertainty is nh bar omega over Q, which is nh bar over Tc. Now, we measure independently, by doing statistics, the fluctuation in the lifetime of the n photon state, and we find Tc over n. Now, if you make the product of these two quantities, you find that delta E delta T is equal to h bar, and so you have a perfect understanding of the Heisenberg-uncertainty relation. It is of course not surprising, but it means that you cannot cheat with the photon box, and you cannot escape this limitation. So I would like to finish with the Schrödinger's cat, because I advertised Schrödinger cat at the beginning, and this is a test of complementarity and decoherence. How can you prepare a Schrödinger cat in the cavity? We start first by realizing that a single atom provides an index of refraction for the cavity field, and if you just send a single atom in the cavity, you change the frequency of the cavity by an amount which depends upon the state of the atom. And the explanation is very simple. Suppose that you have an atom crossing the cavity like that. What we have learned is that the energy of the atom is changed by the light shift effect. So you could look at this curve as a potential curve for the atom. And this means that when the atom enters in the cavity, it is accelerated. Its kinetic energy is increased by this amount. So you have an increase of kinetic energy, which is proportional to the photon number. Where this kinetic energy is coming from, by energy conservation, it can come only from the field. You have n photons. The only way the field can change its energy is that each photon changes its frequency by a small amount, becoming omega minus delta, and so you lose the energy nh bar delta. And when you equate the two, you find that the frequency shift delta is omega squared over 4 delta. In other words, when the two systems interact, the field is changing the phase of the atomic dipole, and the atomic dipole is changing the phase of the field in the opposite direction. And you have an accumulation of phase when the atom crosses the cavity. Of course, when the atom emerges, the frequency comes back to its initial value, but you have accumulated a phase shift. And this phase shift can be equal to pi per atom, which means that a single atom can dephase the field by a huge amount, and the sign of this effect depends upon the state of the atom. So how can you describe the phase of the field? we know from classical physics that a coherent field, which has a well-defined phase and amplitude, is described by a vector in a Fresnel plane or in phase space. So my classical field, the field which has a well-defined phase that I will inject in the cavity, is just a vector, and the tip of this vector will give me the amplitude of the field. This is a classical description. In quantum physics, you have the same description, except that the tip of your vector is now fuzzy because of the Heisenberg uncertainty relation. You have a quantum uncertainty in the photon number, which is the length of the vector, and in the phase, which is the transverse direction. And in fact, the distribution of these tips is according to a Gaussian, and which is shown here in false colors, and this Gaussian is called the Wigner function of the coherent state. So this is just a description, the closest description you have, the closest approximation you have for a classical field. It's just a vector with a fuzzy tip. So what happens to this vector when you send an atom across the cavity? And in fact, we described this in a paper that we published in 1991 with our colleagues Luis Davidovich and Nissim Zaghuri. We showed that a single atom crossing the cavity, if it is in superposition of two states, will prepare a kind of Schrodinger cat for the field. That is, it will prepare a field whose Wigner function will have two coherent components, which I dare call the dead and the live and the dead cat. And in between, you will have fringes in the Wigner function, and these fringes describe an interference effect. I don't have time to enter into technicalities about the Wigner function, but the fact that in the Wigner function you have fringes is exactly the fact that when you send an atom in a Young double-slit experiment, you get fringes. You have the fringes only because you have a coherent superposition. And if you let time go on, after you have prepared your cat, in a very short time you lose the fringes due to decoherence. The fact that the field in your cavity is coupled to the outside world through the loss of photons means that very quickly your Schrodinger cat is transformed into a mixture. So this was a theory. We wrote this paper in 91, and we said that the possibility of photon manipulation through non-resonant atom field interactions opened a domain in cavity QED studies. This was really the beginning of all the series of experiments that I'm discussing today. So the principle is very simple. It's again a use of the miraculous Ramsey interferometer. We prepare a coherent field in the cavity, and then we send a single atom. And before the atom enters, we prepare it in state superposition. Then it crosses the cavity, and when it exits, it imparts two phases at once to the field, and you have now an entangled state. If the atom is in state E, the phase of the field points up. If the atom is in state G, the phase of the field points down. This is exactly the metaphor of Schrödinger's cat. Now, if you detect the atom at this point, you will project the field with one phase or the other, which is not very clever. What you want is to have a cat in the end, superposition. So what you do is that you take advantage of the second Ramsey zone, which admixes the states E and G again. And you detect only after the atom has crossed the second zone. And what the second zone does is that it erases the tracks of the atom. When you detect the atom, you are no longer able to tell whether it crossed the cavity in E or in G. And the result is that you project the field into a Schrodinger cat, a superposition of the two states. So this is the way you prepare it. Now, I want also to tell you that this is a complementarity experiment. Let's look at this experiment as seen by the atom. Each atom is crossing the two Ramsey zones before being detected. And you see that for each atom you have two possible passes. Either the atom remains in state E in the first zone and undergoes the transition from E to G in the second zone, or it undergoes the transition from E to G in the first zone and stays in G in the second one. In other words, the topology of this interferometer is like a Mach-Zehnder. You have two passes for the atom before you detect and look at the probability. But it's a Mach-Zehnder with a spy in it, because the field in the cavity will take one phase if the atom crosses the cavity in level E, the other phase if it crosses the cavity in level G. In other words, if the two final states of the field are orthogonal to each other, they give you an information about the path and the fringes should disappear. And we did the experiment, and you see the result here. As you increase the separation of the phase of the two field components, you see that the contrast of the fringes vanishes. So you are performing here a Bohr complementarity experiment with this Ramsey interferometer. So it's exactly like the Young double slit that I showed in the beginning, except that it's a time domain instead of the spatial domain. Finally, what about decoherence? First of all, in the recent experiments, what we can do is to reconstruct the Wigner function. I have no time to discuss that, but it's a generalized quantum non-demolition procedure. If you send enough atoms across the cavity, and if you are able to displace the field in the cavity in between by various amounts, you have enough information to reconstruct the Wigner function. So you see here the Wigner function of a cat with its two coherent states, and you see the fringes here in between. And we will look at what happens to this cat if you take the Wigner function after various delays. In fact, all this work of ours was triggered by the Wojciech-Zurek theory about decoherence. There was a famous paper published by Zurek in 1991 in which he describes the decoherence of Schrödinger cats due to the coupling to the environment, and this is something which has challenged us to do the experiment. We are very much willing to see that in the lab, and you will see what happens to the fringes. You see here the time scale in milliseconds, and you see that as time goes on, the fringes contrast disappears, and you are left with an incoherent superposition of the two. Again, this is complementarity. This is because the environment, the fact that photons escaped in the outside world, give you information about the quantum path of the system and destroy the superposition. So, and we have been able to show also that the decoherence rate increases with the cat size. If you put 10 photons, you will see a decoherence of about 10 milliseconds. If you put 20 photons, it will go down to 5 milliseconds and so on. And you get to the point where the decoherence becomes so fast that you don't see the quantum aspect, you only see the classical end result. So I think it's time to conclude. I will just conclude by telling that cavity QED can be also performed with artificial atoms. And this is called circuit QED, and it's a field which is developing very fast in many labs in the world. I give you only here an example of cavity QED performed on a chip by the group of John Martinis in the University of Santa Barbara in California. This black stamp here is a Josephson junction circuit which has two quantum states, which plays a role of the two Rydberg states in our experiment. And this qubit is coupled to a cavity which is just a strip line here, a kind of coaxial waveguide, coupled through a capacitance to the qubit, and by playing with this capacitance you can adjust the coupling as you want. You can use, you can use this line to apply pulses to the qubit, and you can use the other line to feed microwave inside the cavity. And so you have on a chip which is 2 millimeters in size, the same experiment that we have in our big cavity. Of course, you have to cool to very low temperature, 20 millikelvin instead of about 1 Kelvin in our experiment. But I don't have time to discuss, but I will just show you a Schrödinger cat obtained in circuit QED as compared to our Schrödinger cat. So it's, and the techniques which are used to reconstruct the cat are very similar. And on this last slide, the decoherence of our cat as compared to the decoherence of circuit QED cat. So this is only one example. Of course, there are many, many things that you can do with circuit QED and not with cavity QED, because in circuit QED you can imprint the qubits on a board, and they are permanent, they don't fly away, they're there for you to study for as long as you want. And you can couple this qubit to cavities and shuffle photons back and forth. So I will stop at this point. I will conclude by saying that I hope I have convinced you that we have come a long way since Bohr and atom and Einstein photon box, but the ideas were there already. We are really on the shoulders of giants, because all what we are doing was there in the principle of quantum physics, and things are moving very fast. In 2007, when this cover of Physics Today was published, we were believing that we still had a lot of advantage over circuit QED. We were very confident. And 4 years later, you have this cover of Nature Physics showing the circuit with here you have two qubits coupled by cavities, and a lot of things can be done. The people working in circuit QED hope that they will one day be able to build a quantum computer. So far, they are factoring 15 with a system with a 48% error rate. which would be very bad for an elementary school child. But for a quantum computer, it's very good, because as you know, the difficult part is factoring. Once you have found a result, you can check whether it's wrong or not very quickly. So even if you find it with a 48% rate, you just have to start the experiment again 2 or 3 times to get the result right, which is okay. But the important point is that if you want to factor a big number, then you would have to control the qubits on this board with much, much, much higher precision that you can do now. So I will stop here. I just want to acknowledge my co-workers. This picture was taken last October, and I stress the fact that I've been working with Jean-Michel Raymond and Michel Boyn for a very long time. Jean-Michel Raymond was my graduate student in the early 1980s, and Michel Boyn in the late 1980s. And I've been very fortunate that they have stayed with me over all this time, because we had really to build this expertise over a long time and to keep the memory of the experiments, and they have had a lot of the seminal ideas came from them. Here you have also 2 very young and talented guys, Igor Dotsenko, who come from the same source as Arno Rauschenbeutel. He was a student of Dieter Meschede in Bonn, and he joined us, and he had been working with you for many years in Bonn. He's a very bright guy, and Sébastien Glaise is also a guy who plays a very important role in our group, and all the other students come from many places around the world, so I'm very, very happy to have been able to work with them. And the last picture was taken exactly in this room 46 years ago, and this was the day the Nobel Prize of Alfred Kastler was announced. And so you see on this slide, on this picture, Claude Cohen-Tanuji in 66, and I am here. So you see people have changed, but I hope that I am not lying if I say that our enthusiasm for physics has remained the same over all this time. I also want to acknowledge the fantastic atmosphere, the atmosphere of freedom and trust which people like Kastler and Brossel, who was working with Kastler in optical pumping, have been able to build in this lab. And this is really a special place for doing long-term research in a very positive atmosphere. And I thank you for your attention.
Here's the first question.
Question I will repeat for.
Yes, okay. What kind of application I see in medicine? I would say I don't see any, but it does not mean that there is none. I think if you had asked this question to Purcell or Bloch in 1946, when they discovered magnetic resonance, they would not have said MRI, because MRI came from magnetic resonance plus superconducting magnets plus computers, and the computers and the superconducting magnet did not exist. So maybe one day, combining ions in traps or circuit QED with something that we don't know about, there will be applications to medicine, but I don't know. And I think this is really the charm of research, that nature has surprises for us that we cannot anticipate.
As you are measuring the numbers of quantum in the cavity, is there some kind of uncertainty Heisenberg relation for the numbers?
Yeah. No. Yes, there is an uncertainty relation between the number of photons and the phase of the field. So as you gain information on the photon number, you lose all information on the phase. We start from a coherent field which has an uncertainty in the photon number and a well-defined phase, and we end up with a field which has a well-defined photon number and no phase at all. So it respects Heisenberg uncertainty relation. And of course you perturb the system because of that. But once you have obtained a Fock state, a state with a given photon number, then you don't perturb it anymore by keeping measuring. Once you are in an eigenstate, it does not change.
So are there more questions? Maybe from the back. I see many students.
The other question.
Thank you. I refer to your slide where you show the discrete steps of photon numbers in time.
Yes.
And you said this is incompatible with the Schrödinger equation. What are the conclusions you draw out of this?
No, I did not say it's incompatible, but I said the Schrödinger equation does not describe the measuring process. And of course, if you think there is a mystery in the measurement process, I agree with you. But so this experiment demonstrates clearly all the postulates in the measurement process, but it does not. There is no explanation for the fact that you get a random result, that there is no way to predict which result you get in the measurement before you have obtained it. And this is what I claim is that this experiment illustrates all what is in a measurement process, including all the mysteries that are around. And the quantum jumps are produced by the measurement, not by the Schrödinger's equation.
Okay. So, are there more questions? Yes.
Yeah. Couldn't you have in your cavity, say, 2 photons, and you entangle them, and with your method you could measure them in principle without destroying the entanglement? Say in advance.
You know, if you have only one cavity, the state of the field is defined by the photon, so you cannot entangle 2 photons in the same mode. What you can do, you need 2 modes or 2 cavities, and we have done experiments in which you can entangle the field in 2 modes of the same cavity. And there have been experiments done in circuit QED by the group of John Martinis, when they have been able to entangle the field in 2 cavities and making a Noon state, a state with n plus 0, n0 plus 0n, a very beautiful experiment which works with n up to 3, and it could go to higher values.
What's the highest precision that you have reached with the transfer of information with these atoms?
You mean in terms of fidelity and things like that?
Yes, like you expect to write something with the E and G states, and you receive the same information that you expected to write.
In fact, we are not very good at that. The fidelity we have in our case never exceeds something like 75 or 80%. One of the reasons that the contrast of our Ramsey fringes is not that good. It's 85 or 90%. And ion trappers are much better. In ion traps, they get much higher fidelity. And I think in the experiments in which photons are used as qubits with beam splitters, you get also higher fidelities. And I think that the people in circuit QED which have permanent qubits can reach also fidelity in the 98-99% range. But our experiments are not very good for that.
So, I don't see any urgent questions anymore, and I know that Serge has been busy since 8:30 this morning seeing research and talking about physics. So I suggest that we just thank him again for his wonderful lecture.
at the end of the lecture, we would like to invite you all for a small buffet downstairs. For that, I would like everybody to go out there on both sides and don't stay at the end of the stairs because the other ones also want to come down. So thank you for coming, and thank you. It was a pleasure having you all here. And there will be another Schrödinger lecture next year, this time at the university again. Thank you.